K2-18B. No, it's not a character from Star Wars. It's a planet 2.5 times the size of Earth and 700 trillion miles away, and it could be home.
The James Webb Space Telescope has done it again. In a groundbreaking revelation that has captured the attention of astronomers and space enthusiasts alike, Webb has released its first real image of the exoplanet K2-12B. Unlike previous representations that relied heavily on models and indirect data, this image marks the first time humanity has truly seen this distant world with such clarity. This moment is more than a scientific milestone. It is a profound leap in our understanding of planets beyond our solar system, challenging the boundaries of what technology and human curiosity can achieve together. K2-12B, located approximately 230 light-years away in the constellation Leo, was initially discovered through data from the Kepler Space Telescope using the transit method, where the planet's presence was inferred by the periodic dimming of its host star. While this method has proven invaluable in cataloging thousands of potential exoplanets, it reveals little about their appearance or atmospheric composition. That is what makes this web-captured image so astonishing. Not only has it brought K2-12B into sharper visual context, but it has also revealed a host of details that deepen the scientific narrative surrounding exoplanet research. Rendered in the infrared spectrum, the image does not offer a traditional photograph as one might expect from visible light telescopes like Hubble. Instead, it depicts a world glowing subtly with the heat from its star, illuminated in fine gradients of thermal light. Webb's unparalleled infrared sensitivity has captured atmospheric haze, heat distribution, and possible cloud formations with unprecedented precision. The image reveals a stark yet graceful world, likely a mini-Neptune based on its size and density, enveloped in swirling layers of gas. The curvature of the planet, the subtle variations in its atmosphere, and the glow from its heated day side create an aesthetic that is as poetic as it is scientific. The implications of this image stretch far beyond its visual impact. This is the beginning of a new era where imaging exoplanets in meaningful detail is no longer theoretical. It is happening. What Webb has accomplished with K2-12B sets a precedent for future discoveries. Every pixel in the image contains information about chemical compositions, pressure gradients, thermal behavior, and even potential clues about planetary formation. From this single snapshot, scientists can construct temperature maps, examine heat distribution between the day and night sides, and hypothesize how weather patterns might function on such a distant world. More significantly, this marks a shift in observational technique. Traditionally, understanding exoplanets has required patience, inference, and cross-verification across different types of data. Webb's image of K2-12B combines spectroscopy, direct imaging, and thermal analysis in a single observational event, the scientific equivalent of moving from listening to a distant echo to suddenly hearing the full orchestra play. This synthesis of data streams allows researchers to move from the theoretical to the empirical in ways that were impossible even 5 years ago. The real image of K2-12B is more than just a visual record. It is an amalgam of scientific revelations encoded in light. The process that led to this image is a marvel in itself. Webb used its near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, to capture K2-12B during a transit, as it passed in front of its host star from our perspective. While doing so, the telescope detected variations in the star's light filtered to the planet's atmosphere. This technique, known as transmission spectroscopy, allowed the telescope to read the chemical fingerprints left by molecules in the atmosphere of K2-12B simultaneously. Webb tracked the planet's emission signature as it rotated into and out of view, using that data to create the first high-resolution thermal map ever generated for this exoplanet. What researchers are finding is just as captivating as the image itself. Early interpretations suggest that K2-12B has a thick, hydrogen-rich atmosphere, possibly laced with water vapor and trace elements of methane or ammonia. The presence of these chemicals points toward a dynamic atmosphere, possibly even weather systems that cycle gases across the surface in complex patterns. While this does not suggest habitability, at least not for humans, it does imply a level of chemical activity that makes K2-12B a rich target for further study. These are the first steps in answering deeper questions about planetary diversity and the chemical signatures that may, in other cases, point toward life. Furthermore, the thermal data obtained from Webb indicates an intriguing level of heat redistribution. For a planet so close to its star, One might expect extreme temperature disparities between its day and night sides, yet K2-12B shows evidence of atmospheric circulation that moderates these differences. This heat distribution implies robust wind patterns and a thick enough atmosphere to support them. These insights not only refine models of K2-12B, but also challenge existing theories about how heat behaves in hydrogen-dominated atmospheres. Until now, such hypotheses were supported mainly by models. Now they are being tested and refined through direct observation. Another layer of importance lies in the way this image reshapes how we teach and think about exoplanets. Previously, much of the public's understanding of these distant worlds relied on artist renderings and speculative visuals. While effective for communication and imagination, those images were ultimately representations, not records. Webb's image changes a paradigm. It provides an empirical foundation for planetary depictions grounded in real data. This will have cascading effects not only on scientific literature, but also in education, outreach, and the cultural understanding of space science. A generation of students will grow up not just hearing about exoplanets, but seeing them in a way that reflects reality. It also brings the field closer to its ultimate aim, finding planets that might support life. While K2-12B is not a likely candidate for habitability due to its size, temperature, and gas composition, the techniques honed here will be directly applicable to future observations of Earth-like planets in habitable zones. The methodologies perfected in imaging K2-12B will be used to observe rocky exoplanets with thinner atmospheres and more temperate climates. Every insight gleaned from this image is a stepping stone toward that larger goal. The goal is to lay the groundwork for the day when Webb, or its successors, captures a real image of a potentially life-bearing planet. This achievement is also a testament to international collaboration and technological excellence. The James Webb Space Telescope itself is the product of decades of planning and cooperation among NASA, ESA, and the Canadian Space Agency. The imaging of K2-12B is not merely a moment of national pride for any single country. It is a human achievement, the result of shared vision, engineering expertise, and relentless curiosity. It exemplifies what becomes possible when the global scientific community pools its resources toward a common purpose. Equally important is the philosophical and emotional weight carried by this image. To gaze at a world 230 light-years away, not as a point of light or an abstract concept, but as a discernible sphere with its own atmospheric identity, is to confront a deeper sense of cosmic perspective. It reinforces the notion that planets are not rare jewels, but common features of the universe, each one a new chapter in the story of cosmic evolution. K2-12B becomes, in this context, a symbol of how much we still have to learn and how far we have come since the days when planets beyond our solar system were mere speculation. In many ways, this single image encapsulates the mission of the James Webb Space Telescope. More than a powerful instrument, it is a window into the unknown. Its ability to reveal the hidden details of the universe, from the birth of galaxies to the structure of alien worlds, demonstrates a profound depth of human ingenuity. The image of K2-12B is a reminder that space exploration is not just about rockets and satellites. It is about vision, perseverance, and the enduring human desire to understand the cosmos. This image also sends ripples through the theoretical frameworks of planetary science. For decades, astronomers have developed classification for exoplanets, super-Earths, mini-Neptunes, hot Jupiters, and more. But these were, to an extent, conceptual containers for planets we had never actually seen. Now, with real images, those frameworks can be tested and refined. K2-12B appears to fall into the mini-Neptune category, but the subtle variations observed in its atmosphere, heat dynamics, and spectral profile suggest that even within this category, individual worlds may diverge significantly in character. This injects a layer of nuance into our understanding of planetary formation and diversity, enriching the theoretical models that underpin the science. The impact of this observation will be echoed in future missions as well. With a blueprint now laid out for how to extract maximum information from exoplanet imaging, upcoming telescopes like the Nancy Grace Roman Space Telescope and the European Extremely Large Telescope can refine their observational strategies. What Webb has achieved with K2-12B is not an endpoint, but a launchpad for a new phase of discovery. These telescopes will build on Webb's foundation, expanding the catalog of imaged exoplanets and deepening the science with even more granular data.